It's going to also be a really unique one because the sun has been crazy active recently, popping off coronal mass ejections like crazy right now.
Like from a scientific standpoint, why is an eclipse special?
So normally the solar disk is, well, it is always very, very bright. But during an eclipse, the moon comes exactly between the Earth and the sun, and so you'll no longer see that really bright surface, and instead you see the corona, which is this outer atmosphere of the sun. It actually expands out into space and, creates space weather and all kinds of things like this. But the corona, the thing is with the corona is it's about 1 million to 1 billion times fainter than the solar disk. So that it's that really high contrast ratio of if you have something that's a factor of 1 million fainter right next to something else that's that really bright source, it's very, very difficult to observe it normally. And so total solar eclipses are this really unique sort of just cosmic coincidence that our moon happens to be in the right place at the right time, such that we can perfectly block it out, and then we're able to see the corona super easily.
But okay, so the corona, so you can study the corona, but why is the corona special?
It's really just one step along the way of how the sun is influencing basically the entire solar system. So, inside the sun, you've got nuclear fusion powering it, and then you've got these different layers in the sun. Eventually you get to the surface, and that's what we can see normally. So there's tons of telescopes that observe the surface of the sun all the time. But then right above the surface, you have the corona, and it's much lower density than the surface, which is why it's so much fainter. And then that material actually is unbounded. So unlike the surface of the sun where it kind of just stays there, the corona actually expands out into space and fills the entire solar system. So if, from a sort of a selfish motivation, we're interested in understanding the corona because any dynamics that happen in the corona will propagate outward and potentially can impact the Earth, other planets, if we have spacecraft, or even if, in the future we want to go to Mars or something, this is the sort of thing we have to think about of like, how is the sun impacting the solar system? And the corona is really this sort of nexus point where a lot of that stuff gets started. And so if you really want to understand how to predict what the sun is going to be doing to the rest of the solar system, you really need to understand the corona. But because we have that trick where it's difficult to observe the corona normally, we don't know that much about it because it's so hard to observe. And so it's sort of simultaneously this really important region for understanding how the solar wind is going to be formed and how the sun is impacting the solar system, but also it's one of the most difficult places to observe. So it's this combination of like, it's very important and it's very difficult to do that make it such an important thing to study.
How does this translate to me sitting in my house in Seattle?
With this sort of data, we can figure out things like temperature and density and other physical properties of the corona. And so basically with these different sorts of data, we can infer a lot of the physical properties of the corona, right? And then the thing is, okay, that is then an observation of what the corona was actually doing at some particular time. So in the long term, we figure out how we can improve our models, which then ultimately will improve our prediction ability so that we can tell you, is there going to be a solar event that is going to be a problem for us here on the Earth? But even more fundamentally, from just a pure science perspective, this sort of thing gives us a better understanding of the complex physics that's going on in the corona, and that could have other applications. Often in science, we work on things that don't necessarily have an obvious, immediate return to the economy or something. But then maybe a century later, someone realizes, oh, all this work that they did does have a huge impact. And you can think back to the people working on the early electricity experiments in the 19th century and stuff. They weren't thinking necessarily about how this is going to be powering all of our society. Yeah. But ultimately, specifically with the corona, it's can we predict not only when these sort of, especially the eruptive events like coronal mass ejections, when they're forming, how they're being initiated, but then also once they've started being initiated, how are they going to evolve and propagate through the corona? And that will have an impact, on where it ends up going, how strong it ends up being, things like this.
If you were to put things on a scale of like 1 to 10, how much do we know about the sun? One being like, we don't even know what that big yellowish looking thing is.
Yeah.
And 10 being, we got everything figured out. Like, where do you think that we are right now?
Gosh, that's such a hard question. Maybe halfway, 5 or 6, maybe 7 if we're being a little optimistic, but we still have a long way to go. I mean, we know a lot of the physics for sure, and we know a lot of the fundamental physics because, people in the lab, especially with quantum mechanics and with really complicated magneto-hydrodynamic modeling and things like this, we know quite a bit. But that said, the sun is absolutely massive. So even if we have sort of the first order, like, we could write some equations and say, oh, roughly this is what's going on. But if you start zooming in deeper and deeper, I'm sure we're gonna find more things that surprise us. Just to give you some context on that, the sun is roughly 100 times the diameter of the Earth, which means it's about 1 million times the volume. So if you just think of how ridiculously massive the sun actually is, you start to realize that, our models are not even close to coming to being able to predict every little thing. But even with these rather simple models, compared to the complexity of the sun, we're still able to get pretty dang close to predicting some reasonable things.
Is there something that, people right now, by studying eclipses, we are trying to find this specific thing out? Or is it more just set this up and let's see what we get?
It's definitely more the latter, which is a little bit different. In most of science, the method is, okay, we have this hypothesis, we want to make a very particular observation to get a very particular result. And we do that to some extent, but in a lot of ways, we're at the mercy of whatever the sun decides to give us on a given day. So the eclipse, they only happen about once every year to year and a half or so. And so that means we're really just getting one snapshot, and they only last a few minutes. So you're really just getting one little snapshot at one point in time, every year or two. But because of that, we end up finding things that we don't expect, like this, maybe there's a really cool coronal mass ejection and it behaves in a way that we've never seen before. And so we can study that. Fundamentally, though, we know what the corona is going to be doing in the sense of we know what metrics we can use to study it. And the main thing are these things we call emission lines. And so this comes out of something out of atomic physics, where different atoms, different ions and elements have very particular colors of light that they'll interact with. And so we know what are the primary atoms that are in the corona that we're interested in. And we know what that can tell us. We know how we can measure temperature and density and magnetic field and something called the Friesen distance and various other physical properties. We know that these lines will give us different information about this. And we know exactly what color they're going to be. It's always going to be the same because the atomic physics never changes. And so we go with these cameras with these particular filters, knowing full well we'll record this line that we're interested in. And then really it's then when you see how bright was the line, how does this line compare to a different line, that's how we then can get deeper down at the different physics that we're studying.
So you can tell by the colors essentially how much of an element is in the sun.
Exactly, yeah. And this is what we do in all of astronomy. So literally any area of astronomy, from galaxies, nebulae, comets and asteroids, the sun, all of it, fundamentally the main tool that we have is to study the light of something. And so we can understand the different compositions, temperatures, densities, magnetic field, etc. We learn that from studying the light. And that's observationally how we do things.
So when you look at this eclipse, is this eclipse special? Or is this kind of like, it's another eclipse? It's great, it's rare, but it's another eclipse.
I think from an observer's point of view, it's a great eclipse, in part because of how long it is. It's going to be at maximum around about 4.5 minutes, especially where I'm going to be down in Texas, as well as we have a group in Arkansas and in Mexico. And at those 3 sites, each one, the time of totality is about 4.5 minutes, which will be by far my longest eclipse. The average eclipses are more like 2.5 minutes. So it'll be kind of weird to go through that 2.5 minutes and then realize there's 2 more minutes to go. For me anyway, that'll be a new experience. Another thing, because it's longer, it basically means the moon is closer. at that time, so it's a little bit bigger, which is why it takes longer to cross the sun. And so because of that, the sky should also be quite a bit darker. So it means you're going to see things a lot more clearly. And then on top of that, there's a really nice planetary alignment. So for the average person, this is going to be a good one to see for all of those reasons. But then also, you'll be able to see Mercury and Venus and potentially even Mars and Saturn as well. So you're really going to see the whole solar system kind of laid out in front of you. And that's something that happened for me in 2017, which was the first eclipse that I saw where it was totally clear. So I had been in Indonesia in 2016, but it was partly cloudy, so I kind of saw it, but it was, it was through clouds and whatnot. But in 2017, it was totally clear. I saw Venus and Mercury and Jupiter, and I saw the corona just stretching out really far across the sky. And I had this profound moment of feeling like that I was just in the solar system, and really, it wasn't this abstract idea anymore. Like, there it was, right in front of me. The closest thing I can describe to it is what the astronauts talk about when they go to space and they look down at the Earth and they get that thing they call the observer effect, where they felt that just profound, philosophical moment of just seeing our place in the universe really viscerally. It's like, I think I experienced something very similar during its total solar eclipse. So I encourage people definitely go, because, that's the kind of experience you can only get either during an eclipse or if you want to spend a heck of a lot of money and actually go into space. Another reason for people specifically in the United States is that this is going to be the last eclipse in the continental US until 2045. So we have more than 2 decades before this is going to happen again in such an easy location for us to get to. So from a convenience perspective, it also is a very good one to observe.
I don't remember exactly, but I remember experiencing 2 of them, maybe when I was really young that was like a total one, because I remember that being reddish and being dark. And then I remember another in 2017 and just thinking like, oh crap, all this is like real.
Yeah.
Right?
Yeah.
Like, oh.
Did you see Totality in 2017?
No, I would have been in Arizona.
Okay.
I don't think so.
Yeah, that wouldn't have been Totality then, yeah.
Okay, but if you're gonna go see this, right, and you've pretty much convinced me, like, man, maybe I should get in a car and go see this. Like, it's gonna be pretty cool.
Yeah.
Where is there like a spot or two that, like, okay, this is the spot. This is where you should be.
It varies a lot. So the path of Totality goes through Mexico, the U.S., and then up into Canada. The reason our sites are going to be in Texas, Mexico, and Arkansas, and the reason we made that choice was in part because the eclipse is longer there than it is in the Northeast, for example. But on top of that, the weather prospects are statistically better in the South than they are in the Northeast. So like in Texas and Arkansas, I think the statistics are roughly 50% probability that it'll be totally clear skies. In Mexico, it's even better probability of clear skies. But up here in New York, Vermont, Maine, these regions, it's more like 80% chance of clouds. So it's really much more of a gamble. That said, I mean, I still think I've been telling people, around here in Boston, I'm telling people, go up to Burlington, Vermont. It's not that far, and if you do see it, even if you see it through clouds, it's still a spectacular experience. If you have flexibility, one thing you could do is get yourself close to the path to Totality and then check the weather forecast like a couple days before and be like, okay, we should drive up there, down there, whatever.
Are you ready for some harder / listener submitted questions?
Sure.
What are some things that we have learned from eclipses? I don't know how your history is necessarily, but are there things that we'd say, because of an eclipse, we figured that out?
Historically, going back into the 19th century, there were a lot of astronomers who would travel to eclipses, and they would very diligently make drawings of the eclipse. And I think usually they would have a team of a few people who would take notes and draw as much as they could. And then they would compile all of their notes to make one master drawing to be like, this is our best guess of what it looked like. And if you go back to those data, it's actually seems pretty accurate based on, I mean, it's not perfect, of course, but it's relatively representative of probably what it really looked like. And then the famous one was in 1869, where they observed with a prism for the first time. So you basically took an image of the corona through a prism, which breaks it into the different wavelengths, the different colors of light. And that was when they discovered this new line that had never been seen before, this new emission line that was in the green at about 530 nanometers. And this had never been seen before. And, in around the same time in the laboratory, chemists had been burning things and looking through prisms, and they had identified many of these different lines, like, oh, this one corresponds to calcium, and this one is magnesium, and this one is lithium, and so on. But this line that they found in the corona had never been seen anywhere else, so they named it coronium, because they thought, oh, it's a new element. And actually, this, just before that, I don't remember the exact year, but that's actually why helium has the name that it has, is that helium was first seen during an eclipse with the same kind of observation, and they saw these lines they'd never seen, and they said, well, let's name it after the sun, Helios, so that's helium. And so that was actually coming from a part of the corona we call prominences, whereas this coronium line was coming from the corona, hence why they called it coronium. And then it wasn't until many decades later in the 1930s that quantum mechanics kind of came to maturity, and they realized that, no, this isn't some new element. It's actually just iron, a very, very well-known element that's all around us, but it's been ionized 13 times. Some of my favorite papers are going back and reading the ones from the 1950s and 60s when they really started getting better and better instrumentation, and they measured all kinds of things about the polarization of the corona, about the fact that there's also a lot of dust throughout the solar system that makes a good amount of the light. There's the electrons in the corona that re-emit solar light, and there's these ions. And so there's some really great papers, like, more than half a century ago, where they were discovering all these things.
Will there always be eclipses?
That's a very good question. So basically, the moon is actually getting farther away from us over time. And this is because as the moon orbits the Earth, it actually creates the tides, right? That's why we have the high and the low tide every day, or twice a day. And that the tides actually kind of rub on the Earth, and there's some friction there. And that actually applies a torque to the Earth-Moon system. And so it actually slowly flings the moon away from us. I won't go into all the physics of it, but basically the moon is, because of the tides, is slowly drifting away. And so if you wait a long period of time, eventually the moon will be too far away where all of the eclipses, it won't be able to fully block the sun anymore. Now, if you run the clock backwards and say what was happening when the dinosaurs were around hundreds of millions of years ago, the moon was quite a bit closer. And so actually you would have had total solar eclipses that would last much longer and would have occurred much more often. So the dinosaurs were probably treated to, a few times a year that they would see a total solar eclipse, and it might last, many, many minutes, as opposed to now where we're, getting just a couple of minutes. And sometimes, like what happened last year across the US, there was an eclipse, but the moon was a little bit too far away. And so you had what we call an annular eclipse, where you get the ring of fire effect. Part of the problem is that the moon's orbit is tipped about 5 degrees relative to the Earth's orbit around the sun. So there's certain times of year where the moon and the sun and the Earth line up perfectly, and there's other times of year where the moon passes above or below the sun. But certainly we are super lucky that we have a moon that is as big as it is, which is much, much bigger than any moon of any other planet that we know of, relative. So the relative size of the Earth and the moon they're far closer in size than any other planet-moon system that we've discovered. So it's probably a cosmic fluke that we have this coincidental alignment. And I've actually heard, jokes where people say, in the far future, if humans really do colonize the galaxy and spread out to different solar systems, then eventually there'll be tourism to come back to the Earth to see an eclipse, because it will be something that they won't have on any of the other solar systems.
Is this a rare type of eclipse? Like in terms of the overall type, or is there an even rarer one that, like, this one only happens every whatever?
So this one is long, at 4.5 minutes, it's a bit long. The theoretical maximum, though, is over 7 minutes. And actually, that's a side note I wanted to make, which is that a lot of people tell me, and it really frustrates me when they say, oh, like here in Boston, for example, we're going to have a 93% eclipse. Like, isn't that good enough? It's 93% is good, right? And I'm like, no, absolutely not. It is completely different because you don't see the corona. You will see a really cool thing, which is the crescent sun, and it's still a great experience, and I'm still, handing out these glasses and telling people, safely observe the partial eclipse. It's a great experience. But that said, if you can go see a total eclipse, that's a whole nother ballgame. That's seeing the corona. That's really fully experiencing it. A metaphor I like to use for this is if you went through a connection in the Denver airport and then you told all your friends about the time you visited Denver, they would say, no, you didn't. You went through the airport. Like, that's a partial eclipse compared to a total eclipse. Like, the total eclipse is going out in the city and seeing everything there is to see, whereas the partial eclipse is like, well, yeah, I had a connection.
That's a great metaphor. That's a great way to look at it too, right? Like, I was in Denver. Like,
were you? Yeah.
What's your favorite eclipse conspiracy theory?
Oh. I mean, if you let me pontificate for a bit.
Go for it, man. Go for it.
So one thing I rather like about both solar and lunar eclipses is it really is a way to prove to yourself that the Earth is actually round and that everything is actually orbiting each other. This was something, that the ancient Greeks knew when they saw lunar eclipses. They saw the shadow of the Earth and they saw it was always curved, and they went, okay, so the Earth is round. So we very much knew that the Earth was a sphere very long time ago. So that's definitely not not true, the whole flat Earth conspiracy. But in terms of eclipses and conspiracies there, oh gosh. I don't know about conspiracies so much, but it is interesting if you read some of the ancient history of people's reacting to eclipses. A lot of people saw it as like a big omen of this horrible thing that maybe, whatever their given deity was angry at them and things like this. There are different cultures who have stories of, monsters eating up the sun, and they would do various things to try to appease their gods, and then the sun would come back. And I can't imagine what that would be like to experience an eclipse without knowing what's happening, because it's really, even knowing fully what's happening, it is a very powerful experience. Some people get incredible fear. I've heard some people almost get paralyzed by fear. Like deep in your brain, something just activates and you get terrified. And for me, I just get immense adrenaline and anxiety. Part of that's probably because of the data we're trying to get, and I'm nervous, oh my gosh, here we go. But a lot of people get brought to tears. I mean, almost everyone the first time is crying afterward. I mean, it's an incredibly powerful thing, even if you know what's happening and know exactly when it's going to happen. I can't imagine if you're just, some ancient farmer somewhere, plowing your field, and all of a sudden the sun goes away. That would be
like, what the fuck? Man, that would be a really terrifying experience, being like, what is happening?
If I recall correctly, and I should have looked up the details beforehand, so I don't know if you want to use this or not, but
we'll give you some leeway. We'll give you leeway.
There was an eclipse where it actually ended a war. So there was a battle going on, and during the battle, a total solar eclipse happened, and both sides thought that this was a sign from their god that they should stop fighting. And so they stopped fighting, and the leaders came together and they made a truce, and the war ended.
I mean, that sounds that's exactly what I would do too. Hey man, we better knock this off. So how did you get into this?
So I went to graduate school at the University of Hawaii, specifically at the Institute for Astronomy. And when I started grad school, I knew I wanted to do something space related, so I was really excited to learn everything about astronomy. But I wasn't sure, what field. I thought I wanted to do exoplanets or asteroids, so I kind of dabbled in a number of different things. And then one day in my first year there, I saw a talk by Dr. Shadia Habal, and she showed some of these just spectacular images of a total solar eclipse and started explaining the science that she was doing with it and the ambition that she had for the coming eclipses, and that she was looking for students to join the group to help out with the instrumentation and do the data analysis and all of that. And after seeing those images and hearing her talk, really passionately about it, I was sold. And I was like, okay, I'm doing it. And so I went on that first eclipse in 2016. And at that time, like, I wasn't even really committed to being a part of the group. It was just sort of a one-off, like, yeah, come along on the eclipse, see if you like it, whatever. And it was just an incredible experience. And also, the more I learned about eclipses and also about coronal science, the more excited I got about, like, that this is a really both important for society and really scientifically interesting area to pursue. And so I've been working with Shadia really ever since. Did my PhD with her, and then I ended up actually doing a postdoc fellowship as well, continuing on our work. And then now I'm at just this last year, I got a professor position at the Wentworth Institute of Technology. And so now I'm trying to get my own students to keep building the group and hopefully carry on the torch of doing eclipses long into the future.
That's pretty much all we got, man. Is there anything that we think we missed or anything like that?
One thing I find really cool about eclipses is that every time you see something different. And this is partly because the sun goes through a cycle where every about roughly 11 years, there's a period of maximum activity and a period of minimum activity. And this is really because of the way that the sun's magnetic field is changing and evolving, and it goes through periods where it's very dormant and then periods where it's very active. And so as you see along the period of different amounts of activity, the corona looks very different. So the magnetic field totally changes, the density changes, whether or not you have coronal mass ejections or what they look like, and the different sorts of structures you see, like, do you see these open field lines that kind of radiate outward, or do you see more of these streamer kind of things that come to like a tip and they're a little more dense? And so because of this, every single eclipse is different. Every corona that you see is different, or really it's the same corona, but every time you see the corona, it's so different. So I'm really excited to see this one because it'll be the closest to solar maximum that I've seen. Like in 2016, I saw it kind of through clouds and it was in the descending phase, so it wasn't so active. 2017 and 2019 were closer to solar minimum, so it was a little bit more organized and not so active. Then 2023 was the last one I saw. That one was very active in Australia. And so that was a really cool eclipse to see, but it was very short. It was only 52 seconds. So I was really disappointed when it ended. I was like, oh, it was so short. I wanted to, So anyway, but this eclipse, it's going to also be a really unique one because the sun has been crazy active recently. Like I've just been seeing things, articles and stuff saying that the sun is popping off coronal mass ejections like crazy right now. So I'm really hoping that we see a beautiful eruption during the eclipse and, and because it's going to be a longer eclipse, it's going to be a bit darker. So combine the fact that the sun is active with a really dark eclipse, and it's also very high in the sky. So I think, like, from an observing perspective, I don't think I've had a better eclipse. So I'm really looking forward to this one.